Wise, just you know, you don't have. I'm not saying you have to join or anything. It's a good investment in your career. I'll just put it that way.
Is it like an Ultrasound Association?
Yeah, it's the Professional Association for Sonographers. Okay, so we've got a lot of objectives today. Diffraction, interference, attenuation. Okay, diffraction is really easy. I'm going to go over this in about 10 seconds. So once we're done with this, I mean, diffraction is easy. Sound spreads out from its origin, right? So if this is the sound wave, and I better watch out for Ivy, it spreads out. I mean, that's diffraction, okay? The farther away from the source, the more it spreads out. There you go. Okay, so we've covered diffraction. Any questions on it? All right. Interference is a little bit different. Interference is simply adding the sound waves. Okay, so if we have two sound waves that interact with each other, they can add up. So if I have a baseline right here, and you can imagine one sound wave is up here at +1, and the other one is down at the same time at a peak here of -1. What is +1 and -1? Zero, okay. What if the next situation, both of them are up here at +1? Yeah, it's going to end up way up here at 2, okay? So they're going to combine. So they're either going to nullify each other at some fashion, or they're going to combine and double, okay? So let's take and then the last scenario is what if they don't quite match up? Okay, so if I have one sound wave like that, and I have another one here like that, what's going to happen? 150%. Yeah. You're going to end up with, at the end of the day, this part from right to here is the same. Then you start adding on some more, so it goes up. And then this one starts taking off, so I don't know, it comes down. And you end up with another wave that's not quite double, not quite zero. It's just another wave where they just add up together, okay? So the peaks, here's a trough, here's a peak, so it'd be somewhere in the middle. Okay, both of them are down here, so actually it should have crossed right through that point or something like that, okay? So waves can add together. Now let me just kind of show you a quick demonstration of waves adding. Let's see where to go. Oh, I lost it. Okay. Yeah, exactly. All right, so here's a ripple tank simulation. And we're going to put two sources on there. Move them a little apart. So you can see as they interact together, you see these what look like radiating lines come out from it. It's just where there's no waves at, right? So they're canceling each other out. And if you want to look at that in 3D, it gets, kind of cool. You can see where they come together, where they cancel out, and where you have the rogue waves off of Africa that knock over the Poseidon, or what was that ship? Yeah. Okay. So that's interference. That's all it is sometimes the waves act together and double, and sometimes they act together and disappear, and sometimes they act together and you get something in between. Interference. Real simple. All right. So we can close that out. All right. Okay, so now the next thing we want to talk about is attenuation, and this is actually going to take us a little bit longer to discuss, and fortunately there's a whole chapter in the book on it, which is chapter 2, coming up very soon. So let's just talk a little bit about what attenuation is before we get to Chapter 2. And then as we get into Chapter 2, we'll go into a little more depth on it. All right? So what did we miss there?
When you said sometimes they act together and double, sometimes they act together and
Cancel.
cancel, then what's the third one?
Sometimes they act together and it's in between. Yeah. Right. If they're exactly opposite of each other, they cancel. If they're exactly the same as each other, they double. And if they're not one of those two cases, it's somewhere in between. So what's on here? Oh, we'll get to that. Okay. So, yeah. So I should do my demonstration. Okay. So if I have two waves, these are fun, and they're identical to each other, what's the result going to be? There we go. So it doubles. All right. So now if I take two that are exactly opposite of each other, add those together, the result's going to be no wave. Huh? Okay, if they're the same, if they're exactly the same, and we add them together, they double. Okay, so intuitively, what is attenuation? Weakening. Any other? Stephanie, what do you think? Absorption, yeah. So as I talk to you, the sound doesn't just keep building in here until your eardrums rupture. It disappears, right? So it's going to disappear through three main means of disappearance. One of them is what we use in ultrasound to visualize things, and that's reflection, right? So if I send out a sound wave in using the ultrasound machine, and we talked about this, when it gets to a interface between two different media, some of it reflects back, right? Okay? So that's reflection. Some of it continues going, okay? Okay, so reflection, and then we could say scattering. Okay? So if I send out the sound wave, it might come back to me, right? If it hits a specular reflector at 90 degrees, it's going to come back to me. But if it hits Ivy and she knocks it off to the side, then it hits Rachel, then no telling where it's going to go, right? So does the sound just keep on going forever? No. Ooh. Nice shot. Scattering. Okay. There's some towels in there. We might have to be careful with this, I guess. Yeah. Yeah, it's okay to hit the equipment. We'll pay for that. Okay. So the last one is absorption. Okay. And of these three, which one is the dominant one in ultrasound imaging? By far, the most of your signal is lost from absorption. Okay. Sorry about that. So this is the one that eats up most of our signal. And okay, so reflection is the sound coming back to the transducer. Scattering is the sound going bouncing off like a reflection, but just somewhere else and not making its way back. What is absorption? This is just the conversion to heat. Okay? So this is loss to friction. The energy basically just turns to heat. Okay, in the scattering, I just want to briefly, we talked about this the other day, two types of scattering, diffuse scattering, okay, and this is what you typically see with something like a liver or kidney. You get echoes back, but they've been kind of diminished a little bit, so this is diffuse scattering. This is the little speckly stuff that we see on the screen. And then Rayleigh scattering, okay? Okay. And Rayleigh scattering is, what's this mean?
It's why the sky's blue.
Yeah, it's why the sky is blue. This means it's proportional. It's proportional to your frequency to the fourth power. Okay? So if I double my frequency, my Rayleigh scattering increases by 16. Okay? Because 2 to the fourth is 16. If I triple my frequency, my Rayleigh scattering increases by how much? You can, I guess, hit it back up here. Thank you. I'll just put that away for a year. Okay, what's 3 to the fourth? Anybody know? 9 times 9 times 3, which is 27 times 3, which is 81? Yeah. It's okay, it's 81. So if I triple my frequency, my Rayleigh scattering goes up by 81. Okay, so it goes up by not a factor of 4, but to the fourth power. Okay, so this is why when we're using Doppler, if we increase our frequency, sometimes we get a lot more Doppler signal back. Okay. And absorption increases proportional to the frequency. So the higher frequency you use, the more absorption you have. We'll save that for next week. We'll get really into what happens with absorption next week. Okay, so if I have an amount of signal that I start out with, and we'll take a random number, we'll say 100%. Okay, not real random, but all of my signal, then after a period of time, I have less signal, okay? And in our case, we're talking about a period of time or an amount of depth that the signal has traveled into somebody. It never really gets all the way to 0 down here. It always stays a little bit above that, but it can get pretty darn close after a certain distance, okay? And as it drops, we measure that ratio of drop in what we call decibels, okay? So a decibel would be, the loss of intensity will be 10 log, and then your initial intensity divided by your final intensity, or your final intensity divided by your initial. Okay. Yeah, this is attenuation. Okay, absorption is a type of attenuation. Attenuation is just the loss of signal, okay? And we give it in terms of decibels, and we call that dB, decibels. Okay, Okay, it's named after Alexander Graham Bell, so the B is always capitalized. So you get dB. And if I lose half of my signal, well, let's figure out what that is, okay? So my initial signal, let's leave that up here. We'll go 10 log, and my initial signal was 1, and my final signal is 5. So anyone have a calculator? They can figure out what 10 times the log of 0.5 over 1, or 10 of the log of 0.5. Well, it depends on what type of calculator you have. Yeah, -3. Yeah, it makes perfect sense. Anytime you lose signal, your decibels will be negative, okay? So -3 decibels, okay? How do you do that? You just take 0.5, you take the log of it, the log of 0.5, and multiply it by 10. Yeah. 10 times what is 0.5 log?
It's -0.3.
0.3. -0. What's 10 times -0.3? You don't need a calculator for that one. Yeah, -3. Yeah. Okay. So anytime we're talking about attenuation, we're talking about negative decibels. Okay, we've lost signal. Okay. Andrea, we good on that? All right. You know how we got it here? Our numbers to put in there?
Yeah.
Okay. Yeah. Okay, the initial goes on the bottom, the final is the result there. We're looking at a ratio of how much it decreased. And we use decibels as our units for that. And we're going to use decibels a lot in here, so kind of get used to seeing this and understanding that what it's telling you is a ratio of where you started and where you finished. Okay, where you finished divided by where you started.
Do you always do a negative?
When we're talking about attenuation, yes, we do. Okay. Let's take our signal down to 1/10 of what it was. All right, so this was 1/2, and this is 1/10. So right here we're going to put 0.1 in there, and instead of getting -3, somebody tell me, what is the log of 0.1? -1. 10 times -1 is -10. Right. So if we drop by down to 1/10 of what we started with, then we have lost 10 decibels. Okay? All right. Let's do one more. Let's take it down all the way down to 1 over 100. Okay? Now, if we do that, we've got 10 log 0.01 over 1, which is -20 decibels. Anna's fast with that calculator. Okay? I'm going to put up another one. I want you to guess at it. We're going to go even 1/10 of that. So 1 over 1,000. -30. Right. Very good. Real simple. Okay, so if we cut it in half, we lose 3 decibels. If we cut it into a tenth, we lose 10 decibels. If we cut it into a hundredth, we lose 20 decibels. If we cut it to a thousandth, we lose 30 decibels. Okay? That's how that works. Our signal has decreased by 3 decibels. It has decreased by 10 decibels to this point. It has decreased to get down to here to 1/100th, 20 decibels. So the strength of the signal has decreased. Okay? Does that make sense? No? Okay, let me find I think I've got a picture of attenuation somewhere. And I don't have it on this presentation. But if we look at our book, chapter 2, first page of chapter 2, and you can just look up here, Ivy, you see how we start out with a signal and eventually it decreases. Okay? So when this is 1/1000th of the size of the original signal, then we've lost 30 decibels. Okay? That book explains it differently? Yeah, I bet it does. I bet it does.
I think you explained it better.
It's another reason I don't use that book. It's a good book, though. I mean,
Yeah.
some people understand it the way I have it here. Other people understand it their own way. So, whichever one works for you. As long as it's working. Okay. So we're good with attenuation now? All right. Okay. So let's move on to, we started out with how the signal decreases. We're talking about attenuation because this kind of follows along the book. Let's talk now about how the signal started, how much power we initially started with, okay? And that's what power is. Okay, here we go. All right. So the power of the signal is just the amount of energy that we're starting with. All right. Power is always given in units of watts. So if you have a light bulb, if it's your reading lamp next to your bed, it's probably a 60-watt light bulb. Right? Okay. If you're trying to light up your dining room, you've probably got maybe 400-watt light bulbs or something around there. Okay, so 400 watts. You're going to light up a bigger room. Now, I don't care if you know what a watt is, but power is in units of watts. Okay, I do care that you know that. Okay. All right, so if we take 100 watts of power, and we're going to take our 100-watt light bulb now, and we're going to light up a football stadium with this one light bulb, what's going to happen? Okay? We're not going to do a very good job. One light bulb, when you're sitting in the cheap seats where I get my tickets, you're going to be unable to read your newspaper. So it doesn't work. All right. This is now we're talking about intensity. We're taking the same amount of power that we might have had for a reading lamp or for our dining room, and we're spreading it out over a huge area, a really big area. And the intensity just drops right down to almost nothing. Okay? Now if we take that same power, 100 watts, I've written up here 400, so we'll make it 100, just to be consistent with the slide. Okay, so we take 100 watts, and now we're going to focus it as a laser. All of that light's going to stay in one little bitty area, okay? Now then, is this enough energy to light up a football stadium? No, but we've increased the intensity by reducing the area to the point where 100 watts of power can actually cut through steel. It's still light, but we've just reduced it down. We've focused it down to one point. Okay? So our power divided by our area equals our intensity. Okay? So if I ask you, what is intensity, what will you tell me, Martha? Power divided by area. And Stephanie, if I increase my area, what happens to my intensity? It decreases. And if I increase my power, what happens to my intensity? It increases. Okay? So power divided by area is intensity. Does that all make sense? All right. Now let's go back a couple more steps and talk just briefly about what power is. Okay, so we really have to know what power is, what we're really talking about with power. Okay, we're talking about, there's a knob on our ultrasound machines that says power, right? What does turning that knob do? Increases or decreases the power, but actually what it does is it increases or decreases the voltage. Okay, we'll just say the volts that are going to our transducer. Okay, volts, temperature, these things that we can measure, voltage, temperature, what are some other variables like that you might measure? Amps, perfect one, yeah. Okay, these are all amplitudes of something, okay? The amplitude of my voltage is maybe 10 volts, okay? The amplitude of the temperature in here right now, it feels like it's about 74, okay? That's a measurement, that's an amplitude. So volts is given in an amplitude of some unit, okay? Of some unit, of whatever it is. Amplitude, okay? And then the power is proportional to the amplitude squared, okay? So power is proportional to amplitude squared. In electricity, you would say it's proportional to the voltage squared. Okay? The amount of power as you're walking across the desert in the middle of the summer and you forgot your canteen, the amount of power from the heat around you, the power from that heat is the temperature squared. It's proportional to it. Okay? So if I double my voltage, what happens to my power? Not quite half. Does something else. It doesn't double. It'll go up by 4. Right. So 2 squared is 4. Okay? If I triple my voltage, how much does my power change? Changes by a factor of 9. Right. Okay. So power is proportional to the amplitude squared. All right. So that means intensity is, I won't say equals, but I'll say in here, I'll say it's proportional to amplitude squared over area. Okay? Okay, now because of this factor that power is proportional to amplitude squared, remember just a few minutes ago I showed you that 10 log of the initial or the final intensity over the initial intensity. Okay, we saw that. Well, if instead of using intensity in here, they use watts or power, they say, what is the decibel change or the attenuation when the power has changed by so much? Well, it's a little different because intensity is proportional to the amplitude squared, but the power, you have to square this in order to, if you put power in here, I'm putting in P's for power, then I have to square this, okay? Now, you don't have to write this down yet. I'll tell you when the important thing to write down is. If you remember how logs work, and we kind of briefly talked about this last semester, I know you weren't here, but if I want to find out the log of something squared, I can take this exponent off of here and put it out front, okay? So anytime I'm talking about the decibel change, the attenuation with power, I have to use a different formula, 20 log of power final over power initial, okay? This is what you need to write down, this part here. Okay, so there's two different types of decibel equations that you're going to have to learn. One of them is specific to power. Anytime they use power, they use watts. You need this one. Okay. The other one, 10 log, and then I'll just say amplitude final over amplitude initial, is good for everything else, okay? So this is the power case, and this is the everything else case, all right? All right. So when you take your exam, if it says power, you just got to put that 20 out there instead of the 10, okay? Okay, in this, yeah. No, we're still on chapter 1. This is pretty much right off of page 19 where they're talking about decibels, but I'm kind of going out a little bit and talking about the power formula for decibels and how we get to that before we move on. I don't want you to get too focused on decibels, but there are two versions of this. You may see that come up somewhere, and you need to be aware of it. Okay. Okay, the next part of your book talks about the half value layer. Just ignore that. We'll get into that with attenuation. Okay, and I don't know anybody that talks about half value layers in ultrasound except for these guys, so moving on. There's nothing to see here. Move on. Briefly, let's talk about penetration. Okay, the higher your frequency, the better penetration you're going to have, the better your signal will travel through something. Did I say that right? The higher the frequency, the lower your penetration. Yeah, the higher the frequency, the less penetration you get. Excuse me, sorry I messed that one up. Lower the frequency, the more penetration you get. Okay, that's why they do skulls on adults. They go through the bone at 1 megahertz. Okay, they use a very, very low frequency to go through a skull and do a transcranial Doppler. Okay, now let's get into echo ranging. All right, echo ranging is a little important. So when we use sound in the body, we don't, our transducers are not firing out constant sound, okay? So if we have constant sound, we end up with a situation where if we're trying to determine how far apart these mountains are, and we just keep transmitting sound, and we're waiting for these echoes to come back, what happens? Eventually, all the echoes are blending together, right? So you can't tell how far apart the mountains are because everything's just blended together. So what do we have to do in order to find out how far apart these mountains are? We could walk to the mountain and walk back. That's one way. Go to the next mountain. That works. Okay. Now, those of you that were in the lab yesterday, the second part where we fired the horn and we listened for the echo to come back, the other sound, what would have happened if you had just kept holding your finger down on the horn? Would you have heard that sound come back? No. Okay, so we have to send it out as a short pulse. Beep, right? That's how we have to send out our sound. So we use pulses that go out. It bounces off of tissue, it bounces off interfaces, and comes back to us. So we send out a pulse, we listen for the echoes to come back, we write down on our machine how long it took for each echo to come back, and we plot that as the depth into the patient. Okay? Now, we don't actually write it down. The machine does that part for us by plotting on the screen how deep it is. Okay? But it assumes that it went in at 1540 meters per second. Whatever it bounced off of, it just counts seconds until that echo comes back, and then it says, okay, well, this took 4 milliseconds. It must be at a depth of about 0.75 centimeters. Okay? If it takes 13, is it milliseconds or microseconds? I can't remember. Microseconds? Yeah, and then it's going to be at a depth of about a centimeter. Okay, so every centimeter it takes for sound to go in and back takes about 13 microseconds. Okay, so we'll figure out how that works in just a minute. But just looking at this, now here is, we're measuring the mountains using a small pulse, and can we determine how far apart each mountain is? Can we get pulses back from each one? Yeah, it's pretty easy, isn't it? Little pulse comes out, mountain 1 sends back a pulse, then mountain 2 sends back a pulse, and then mountain 3 sends back a pulse. Okay, so that's how we use ultrasound to tell us where those interfaces are in the body. This is known as echo ranging. Okay? In your book it's called echo ranging or sound ranging. What do you have to know in order to determine exactly how far from our transducer here, Mr. Swiss Yodeler, the first mountain is? You have to know the speed of sound and the medium it's traveling, which is air, I don't know, about 330 meters per second. Okay, if this is soft tissue, how fast is it traveling? 1540, right. What else do you need to know? The time. The time from when he sent out the signal till it got back to him. And then you can calculate how far away it was. All right? So let's do that real quick. Anna's still got her calculator out. So if we have an interface that's, I'll pick a number between 1 and 20, Stephen. 17. Okay, 17 centimeters in the body. And our transducer is here on the surface of the skin, and we send out a little pulse. Beep, beep. And we have this down here. Let's make it a specular reflector. How's a specular reflector going to be? Flat and larger than my sound. Okay, good. So the echo is going to come down here, hit this, bounce back, and come back to here. All right. So how fast is it traveling? This is soft tissue. So 1540 meters per second, all right? And our distance is 17 centimeters plus 17 centimeters. So our sound has to go 34 centimeters total, right? So we know our rate, we know our distance, and we should be able to figure out the amount of time it took to get there. So we would do that by taking 34 centimeters divided by 1540 meters per second, and we get how much, Anna? Seconds? Or did we?
You take into account the centimeters 10 to the 2. So that's add another 10 to the 2 is just going to be 10 to the minus 6.
Okay. So 6.5 times 10 to the minus 6 seconds, or we can rewrite that as 6.5 microseconds. Okay. No, we added 2. We went from 10 to the minus 4 to 10 to the minus 6. I'm going to let Anna do all my math from now on. What?
Did she do all mine too?
You got to take that up with her. So it takes about 6.5 microseconds. Does that sound right? I'll have to look that one up. Yeah, I'm thinking maybe it'd be closer to 65. Anna's about to lose her.
I'm going to lose my job right now. Yeah, it's 22.
22 microseconds. We still got to add another 0. We're finding the amount of time it took to go 17. Yeah. Time is going to equal the distance divided by the velocity. Yeah.
This is where they lost me in the homework if they're recording.
Okay.
Something to the micro.
And this is where the Edelman book really, really shines. Okay? Here's the other way to do it. If you go a distance of 1 centimeter, it takes 6.5 microseconds in soft tissue. To go a depth of 1 centimeter, there and back again, it takes 13 microseconds. Okay? To go a depth of 17 centimeters, it takes 13 times 17. Or it takes 6.5 times 34. So if you're asked to find how much time it took, this is the easy way. Okay? To go 1 centimeter, it takes 6.5 microseconds. To go 1 centimeter depth, which is, remember, you have to do the round trip, and it takes 13 microseconds. I looked in the book, it was right there. But this is actually fairly well known. Almost every sonographer memorizes it right before their SPI exam. It just works out. So you can actually calculate this by replacing in our little equation here. You can put a 1 in there, and that's how you would come up with the number. Okay? If I put a 1 here and I do this calculation, I come up with 6.5 microseconds. Okay? If I put a 2 here, of course, this doubles. All right? So that's where it comes from. I wanted to show you the tough way to do it, and then show you if you want to do a little memorization, you can do it this way. Okay? And that's how we can find out how deep things are, okay? So we just figured out how much time it takes to go 17 centimeters, all right? What the machine does is it counts the time and then says, oh, well, you went this far, okay? So if it takes 56 microseconds for the signal to go from the transducer to the interface and back, then how deep was the interface? Spend 1 minute to figure that out for me. Okay, we're looking at 56 microseconds for the sound to go from the transducer to the interface and back. How deep was the interface? 4.3. And then how, meters? Centimeters, thank you. Okay. Yeah, so you just take 56 divided by 13 equals 4.3. Yeah. right.
So 10 stars. So you're not gonna access anything that's not soft tissue? Because I have a
Right.
that's like bones.
You probably will need to figure that out, at least one question on the SPI exam. When I took my last registry exam, which was for vascular, they had one question that exactly was that. It was, how deep in bone are you going? And it's like, oh, give me a break. And it gave you the numbers. It said, okay, bone is 4,000.
48.
Yeah, it gave us 4,000 because we don't get calculators in there. You know, it gave us numbers we could work with. It said bone is 4,000. How deep was it, or something like that? And I was like, oh, poof. Yeah. I figured I knew enough of the rest of the stuff. I didn't have to worry about that one question.
Yeah.
So just so you know, I want to just show you real quickly before you take off. This is, we're still echo ranging, but we've given it a longer pulse in this case, okay? And there's still some separation between the pulses as they come back. So we're still using pulses. It hits the mountains, and we can still separate right here the two closest mountains, all right? Now, I think I've got the third case on here, just real briefly. Now we're still using a pulse, but the pulse is just a little too long, and you can see that these two get interfered with, and we can't separate them with our ultrasound machine anymore, or a yodeler, all right? So keep that in mind. That's called range ambiguity. The pulse length is too long. It gives you range ambiguity. Okay, we'll go on into that in about a chapter and a half here or whenever. Thank you. Good day?
Homework to do?
Oh, yeah, hand up the homework. Huh? For what? For this? Yeah, distance divided by velocity equals time. Okay. What do you need? A calculator?
I mean, stapler.
Yeah, I got calculators. You don't want mine, though.
Stapler.
Trust me. There's also a stapler in the lab, just so you know.